All right, so this week in the parent class, we're talking about U substitution, or also just known as substitution, which is a technique for evaluating integrals. Last week we talked about 4.1 in the parent class, where we learned about integration and antiderivatives. So everything that we're doing in the support course this week is just practice with what we did last week. There's no additional prerequisite skills that are really worth delving into right now. However, because chapter 4 is all about integration, the more practice we get, the better. So we're going to just do 3 different integrals today for practice, and then the assignment for this week will have more for you to do. As of right now, for this section, we're going to assume that you don't know how to do U substitution, because that's what we're covering in the parent class this week. And generally, the support course is not supposed to assume that you know what we've already done in the parent course for a given week. So instead, we're going to just use the techniques of 4.1. However, sometimes we might have to simplify our integrand a little bit before those techniques are actually usable. So let's start with this first example. I want to take the integral, which remember is the same thing as the most general antiderivative of this function, x squared minus 4x plus 19 all over 6x. So in order to do this problem, I can't really work with it the way that it's written because it's given to me as a quotient, and I haven't learned any rule that kind of does the reverse of the quotient rule for derivatives. Remember, if we're taking antiderivatives, that's basically like taking derivatives in reverse. But we haven't learned a way of dealing with quotients in kind of a general sense. However, this integral can be split up into, or this integrand, sorry, the function inside the integral, can be broken up into 3 separate terms if we split the numerator. So I can write this as x squared. Actually, I'm going to do a couple of things. Before I jump to that, this 6 down here is really like a 1/6, because that 6 is in the denominator. And we know that you can pull constant multiples out of integrals. I'm going to pull a 1/6 out. I meant to do that first. That would leave me with just an x down there. Okay, so now we just have that x. I have x squared over x as one of those terms, minus 4x over x as another one of those terms, plus 19 over x as another one of those terms. Dx, okay? This can be pretty drastically simplified. X squared over x is the same thing as just x. 4x over x is just 4, so we have a minus 4 here. And then this guy right here, you don't need to do this, but it might help if you're getting used to, if you're still getting used to integrals and antiderivatives, to pull the 19 out front so you see a 1 over x there. And I'll talk about why that might help in a second. But let's go through and find this antiderivative. I have this 1/6 here. One of the things that we learned in 4.1 is that if you have an integral of a sum or difference of functions, you can take that corresponding sum or difference of the integrals of those functions, meaning I can integrate this term by term. That's what that means. So what is the integral of x? It's not 1, that's the derivative of x. I want the antiderivative. So we think of the power rule in reverse. I'm going to add 1 to the exponent, which is, right now the exponent is 1, so adding 2 to that gives me a 2. Then I multiply by the reciprocal of that number that I just put up in that exponent there. That would be 1/2. And remember, again, as you're getting used to doing integration, it's always a good idea, if it's reasonable to do so, to mentally take a derivative of what you get to see if it takes you back to what you started with. So the derivative of this, x squared, that 2 would come down, multiply to the 1/2 and give me a 1, and then I would subtract 1 from the exponent, which all comes down to just x. Okay, so I'm not going to talk through that every time, but it's a good thing for you to be doing as you move along. Constants, we know that the antiderivative of a constant is that same constant times x, or whatever your variable happens to be. And then here's the reason why I wanted to deal with this, or write this 19 here. So that 19, when I take the integral of just this term, can also be pulled out of my function, and that leaves me with just 1 over x. We know that the antiderivative of that is the natural log of x, except there's a 19 being multiplied to it. So it really comes out to 19 times the natural log. And I said the natural log of x, but really what I should have said is the natural log of the absolute value of x. In the parent class last week, we talked about why that has to be an absolute value. And then because we're looking for the most general antiderivative, we're going to include this plus c here. So this is my final answer. Don't feel the need to distribute that 1/6 in there. There's no real reason to do that. It's fine to leave it in this form. So that's going to be my answer. Let's jump to another problem. This one here, we have the integral of 6e to the x minus 5 to the power of x plus the cube root of x to the 4th power. So this is not a terribly difficult integral to do. We're going to do it term by term. But one thing I would probably change about my integrand is this radical here. I know it's going to be easier for me to deal with this integral if I write this in the form of a rational exponent. This is the same thing as x to the 4/3 power. In that form, I have an easier time figuring out what the antiderivative should be. So, okay. Remember, we can integrate this term by term, and if you ever have a function times a constant, then the antiderivative is just that constant times the antiderivative of the function. So this is going to be 6, and then remember, e to the x is its own derivative, and that means it's also its own antiderivative. So I get 6e to the x. I get exactly what I started with. Not the case for 5 to the x though. In the parent class in 4.1, we talked about how this would equal 5 to the x over the natural log of 5. Or you could write it as 1 over the natural log of 5 times 5 to the x. Either way you want to write it is fine. And then another power function, we dealt with one of these in the previous section. Add 1 to the exponent. Like 3/3 is the same thing as 1, so 4/3 plus 3/3 would be 7/3. Then multiply that by the reciprocal of the number you just put up in the exponent, 3/7. Finally, include your plus c there. Okay, that's the most general antiderivative for that. Last problem. Okay, I have the integral of 2/3 x cubed times x squared minus 3 to the 2nd power. This is a problem that you might have some success using that substitution rule or U substitution, which is what we talk about this week in section 4.2. But at the beginning of this video, I said that we're not going to assume that you know how to use substitution. So instead, we need to approach this using a more elementary technique. And if you look at this, it's a product of two functions. I can't take an antiderivative of a product. We haven't covered any rule for general products of functions, and we're not going to in this class. But you can expand this whole thing out, since it is just a polynomial, and then integrate it term by term like we've kind of been doing. So very first thing I want to do is take the 2/3 and pull it out of the integral. I have that rule that allows me to do that. Okay, then I'll have this x cubed here. This x squared minus 3 is being squared. I'm going to square that and leave that part in parentheses. So that's going to look like x to the 4th minus 6x squared plus 9 dx. From algebra, you really should have the ability to square a binomial like this without having to write out a bunch of steps. You should be able to go from here immediately to here the way that I just did. And that's an algebra skill that you really, you should have mastered before even coming into this class. Okay, we're still not ready to actually take any antiderivatives. What I want to do is distribute that x cubed into all three of those terms. So that's going to look like x to the 7th minus 6x to the 5th plus 9x cubed dx. Okay, finally, now this is in a form where I can integrate it term by term. I have a sum / difference of terms here, each of which is a power function, which are straightforward to integrate. So I still have my 2/3 here. When I integrate this thing, I'm going to add 1 to the exponent and then multiply by the reciprocal of that, so 1/8 x to the 8th. Same thing here, I'm going to add 1 to the exponent, which is 6, and multiply by the reciprocal of that, which is 1/6. There's already a 6 there, so 1/6 times 6 is just 1. This becomes minus x to the 6th. And then finally, I'm going to add a 1 to this exponent, so plus x to the 4th now, then multiply by the reciprocal of that, 1/4. Multiplying that to the 9 that's already there would give me a 9/4. Then I have this plus c. Don't forget your plus c. Okay? That's it. Okay, so this section, again, it's nothing new. It's nothing as far as prerequisite stuff. It's nothing that you've seen in like a previous class. This is literally what we were doing last week, but it's worth the time to just get some additional practice on it. So that's all we have for this week.